by how enthusiastically trying I can feel that just about. Yes, I can relate to that. Yeah, but hopefully today's session will be all right. I've been drowning in work, but I've done PCBs before at least, so I've not needed to do as much prep as I did for those machine learning ones. Those ones took a lot of preparation, and I still feel they were a little rough, but that's all right. Hopefully they were tolerable, and they will improve in the future. Survived. Excellent. Yes. That is the primary verb I feel for my life right now. Just surviving. Lovely. Okay. Well, it's 6 past, so, well, nearly 7 past, actually. So we should probably get a start, I suppose. I feel this session will be more laid back than the machine learning ones. Return to our basics of playing with CAD programs, although these are, well, this is a CAD program for drawing circuits and things, so it's quite different than Fusion, but shares a lot of, I guess, the similar feel. So, on that note then, we'll start with, of course, the classic fun admin-y things that everyone really enjoys doing, as I'm sure. So I'll send the attendance form. I've saved the link ahead of time. Wow, how responsible. I'm like 20% sure that's the attendance form. Let's double check. Yes, it is. Excellent. Cool. So yes, please fill that in just with your name, so we know that you've rolled around. It's always good information to have. And additionally, I sent it around last week as well. Just continued reminders about the AGM. So there's the form for registering your interest in the AGM if you are interested. So we've had 4 people reply so far, which is a good start. It sounds like 2 to 3 of you will be able to make the AGM at least, which is good. And then for the positions that people are running for, 1 person is up for either running for secretary or treasurer. Unfortunately, 1 person can't be several, so I guess that's just for either of them. And a couple people said they're just coming to vote. I would encourage anyone, though, who will be around next year to run for something. It's pretty fun. Goes on your HERE report, so, you know, when you graduate, it'll say, hey, look, I led such and such team, or I was the society treasurer, secretary, etc., for whatever. Yeah, there are all the things available. So all the different project leads and all the different society roles. Because the entire committee is either graduating or going on industrial placements next year. So we'll be around to help in the transition period, which sits shortly after this AGM for the rest of this year, and then we'll be able to like support remotely, probably, things next year if you want help as well. But the society is running slightly low on leadership, so gather your friends, family, co-workers, anyone you can, you know, get to legally run for a uni position. Do it. How's the pay? Let's see. I guess you're paid in experience. Yeah, it's one of the one of those things. Although, with that being said, if we manage to secure as much like funding as we did this year, the people in charge of things, if you do want to, like, for example, build some really cool thing, you've got a really good idea for one of the projects, there is a lot of money that the society can sign off on you spending, as long as it's for, you know, the general realm of the project. So, yeah, I don't know. I think it's fun. I think, especially you 3, seem very, very dedicated, because I see you around a whole bunch, and I know you're doing stuff for the other projects as well from time to time, so you'd be excellent committee members if you're interested. So, if you are interested, go ahead and register your interest there. It's non-binding. We're not going to hunt you down if you're like, I'm interested in this, and then decide you're not. It's just to get a feel. Cool. So, that's that form, and then feedback that I got for the machine learning things were alright overall. I probably could have, well, the pace of instruction has always been a little bit fast, I think, for all of my lessons, so maybe I'll need to find a way to slow that down a tad bit. And somebody left the suggestion that practice sheets would be a good idea, and I agree with that. I didn't put them together because I did not have the time, but what I will do is I've written a nice little note for myself. So over Easter holiday, for anyone interested, I will go hunt down or create some practice problems for different machine learning things. So if anyone wants to practice on that, hopefully I will have some material for it. Of course, you're always free to use the data that we have in like the ARM project repository that I was kind of recreating in those sessions. That data is there, and you can build models with it and start at what I have and try and make it even better if you'd like. Awesome. I think that is all the little rambly admin stuff. So I think we can pop on to doing some circuit design or PCB design. Cool. Yeah. So we'll start then with talking about KiCad, I guess. So, yeah, well, I've already closed the website, but I'm going to reopen it. Thanks, just in case. I've also now discovered I have this lovely thing in my preferences. Thanks, Firefox. You can set the default zoom on all web pages to 150, so you can see everything. It's very nice. And I can show you KiCad. So, KiCad, I think it's pronounced KiCad. Depends on who you talk to. The people on the Avalon rover project say KiCad. That's where I learned KiCad from. But yeah, it's a nice open source thing that you can use to design both electronic schematics, but also the PCB boards. And it can do like basic rule checking to check if your things are electrically sound, and it even has a way of 3D visualizing things, which is pretty cool. So it's a really excellent program. You can use it for really basic or really complex things. Like I said a moment ago, the entire Avalon project, which makes underwater rovers and for competition in the society, that student project in the university uses this to make all their stuff. It's what I've used before to make the PCBs that I've shown off a couple of times before, these tiny little motherboard things, which actually we could probably take a look at in KiCad today. But excellent to use. I'd recommend downloading it. If you want to follow along, you can download it on any platform you want. And then they've also got some additional libraries here that have, well, are places that you can get extra little symbols and things, and we'll see what all those mean in a second. Cool. Okay, that's probably all I need to do in a web browser at the moment, so I will reset my zoom and pop out of there. Cool, and we'll open KiCad. So there we are. And I will create a new project. So you can go to New, and Project. Ooh, I've just realized this might be a bit teeny, actually. How big is this, and can everyone see it all right? Or is this a bit small, and would it be nicer if it were larger? Like these text up here in the menus and stuff. A little small. Okay, well, let's find out if we can make it a bit bigger. The answer is maybe, actually. Icon scale we have, well, that might be what I'm looking for, but I don't really know. Let's see what happens if I do that. Okay. Did that change anything at all? Yeah, it might be a bit teeny at first, but... So the text has remained small. The icons have become large. I will try that as the last thing, and if that doesn't work out, then it's alright, because most of the stuff we will be doing doesn't rely on that. Yeah, okay. That's being a bit squirrely. Sorry about that. I actually probably should have checked that beforehand, but that's alright. It's not too bad. You'll see we can zoom in on the actual thing once we're doing it. And I'll be sure to read out any text that I'm clicking on verbally, so even if it's small, hopefully you can follow along. So, on that note then, sorry about that. If you go to File, which is the menu up here on the top left, and then down to New, in those options you can have just a new project or a new project from a template. So you can start with templates, which is really cool if you're making similar circuits all the time. I'll just do a new project totally from scratch, so that's also Control-N as a little shortcut. Pick a place for it to go, call it Bootcamp, put that in there. And now, over here on the left, again, maybe perhaps a tiny bit small, but it says bootcamp.pro, which is project file. And then you have two other ones here, a .csh, which is a schematic, and then a .kicad PCB file. So as they said, well, as the names imply, one of these is for drawing the schematics of your electronic circuit, and then the other one is for turning those schematics into an actual circuit board. So first thing we're going to need to do is draw a schematic. So for that, we have this big schematic button here. We can go ahead and click that, and that will open up one of these sub-programs in KiCad, which is this one here. And this one allows us to do schematic design. So this one, it's got a load of buttons around, so you can use it graphically. I'll probably be pointing out as I go along the keyboard shortcuts for things, because lots of things, of course, in CAD are repetitive, so it's good to have these keyboard shortcuts on hand. So I'll be sure to point those out as we go along. Additionally, just as I guess a bit of a context, I suppose, what I will probably be doing today is following mostly, but not entirely, along with this tutorial that you can find here. And I'll be linking this, of course, in our after material, but what this project is doing is creating a small little development board. So think like an Arduino, and it's creating this simplified little Arduino kind of board using this processor here, which is an ARM processor. I'll talk a bit more about that in a minute, briefly, but not too extensively. And it's our job to take this, chip, add all the extra components that we need to make it actually useful, then put it all onto a board like this, lay out all those traces, and then what you can do is send the files that you get out of this process to some sort of fabrication company, and then you get back in the post a bunch of these little circuit boards that look just like this, and then you can buy your components separately and then solder them all together. So it's a pretty easy little process. I've gone through it once or a couple times before. But yes, so that's just for context. Our end goal is to produce something that looks a little bit like this, where it's a tiny development board. Think of it as a baby Arduino, like an extra teeny Arduino, that you can write code for, and it has 8 GPIO pins here, an LED built in somewhere here. Yeah, an LED in there somewhere. Yeah, there it is, diode 1. Obviously, this doesn't have any of the components soldered onto it yet, but you'd solder things on in the end. Awesome, cool. So that's the context of this, I suppose. So let's get started. I introduced you briefly just to the structure of KiCad. It's built or split into those separate applications. So this one's called a schema with 2 E's in front of it, and that's for doing schematics. If you go back to the main window and you press this other button over here, that's the PCB designer one. That pops open a different window. Yeah, this one here. You can see it looks quite different, and we'll go over how to use this as well. And this is how you actually lay out the physical arrangement of the parts on the board instead of just the electrical schematic. Cool. Nice. So here's our schematic place, and the first thing to do is, well, since we're building a little development board for a particular processor, probably to add that processor. So first shortcut for us to learn, and I'll zoom in a little bit so you can see this this little grid here. Maybe you'll be able to see. I just noticed the compression might be making that a bit hard to see, but it's a little grid, so it snaps things by default. If you press A, the A key, that will add a symbol, and you can see you get this big symbol library. It says up here it's loaded 16,000 different items. That's because my KiCad installation has all of the additional libraries, one of which actually contains this processor that we're about to use. So if yours does not, I'll show you how to do that in just a moment, how you would get that library loaded in, I mean. But for mine, which has everything, I just need to search for the processor we're using, which is the ATS, AMD. It's one of these microchip SAMD things, and we want the 10C14. So there we are. That's what we're looking for. You can see it sometimes stores a bit of information. I'll read this out because I know the text might be small. So it says it's an ARM Cortex M0+. That's just the type of ARM processor. ARM processors are the ones that are in your cell phone or in lots of these development boards, lots of Internet of Things devices. It's a 48 megahertz chip. It's got 16 kilobytes of flash memory built into it. It can run on anything from 1.6 to 3.6 volt power, so that's something to keep in mind, that 1.6 to 3.6, because we'll need to supply it with that power later on. It's got 12 GPIO pins, although 2 of those are for programming, so it's not really a GPIO pin. And it also has this thing here, SOIC 14. Things like this, that has to do with the shape of the physical chip. We'll see that later, because that's not really connected to schematics. But yeah, anyways, once that's selected, you can go ahead and click OK, and load it in like that. Now, if people are trying to follow along, which I'm actually not entirely sure if you are, so I'll do a quick poll trying to see who's following along. So, who will be trying to follow along? Okay, that's a Discord poll. Hey, look at that! I remember how to use the poll robot today. Making big steps. Excellent. Okay. In that case, who was able to just find this chip? Was that available for you all? So I'll ask that as a separate poll. Have you found this chip? It's the ATS AMD 10Z1 something. And if you haven't been able to find it when you just typed the A button to pop up your menu and you search for it, you might not have it installed. So I just want to know if you do or don't. And if you don't have it installed, I will show you how you do that, because it's not too hard. So has anyone found it? There are no responses either for or against that question, so maybe people haven't tracked it down quite yet. A little late, but it's there online. Oh, yeah. Yes, so I think to follow along with things directly, yeah, you'll probably need to use this downloaded version of KiCad. I don't think it's too bad to install if you want to try and install it. I probably can't, I guess, wait for everyone to do that if no one's done it yet. But yeah, you're definitely free to do so. You can get that just from the KiCad website. So if you just search KiCad, there you are. Download button's right on the front page, and hopefully that shouldn't be too bad. That's for Maria's question, and then for Philip, who hasn't been able to find the chip just yet. For that, I will send this link here. This is a link to one of the libraries that you can install for KiCad. So if this one isn't installed by default for you, it holds 86, symbols, it says here, for these different microchip controllers. Now, microchip is actually a name of a company, despite the fact it's just also a normal English word. But yeah, they're a company that makes, now this might blow your mind, microchips. So they're the ones who make this particular processor that we want. From here, you can click this download microchip SAMD 7-zip file. Just thought, maybe most computers should be able to open 7-zip files. If you're on Windows and can't open a .7z file, then yeah, you might want to install 7-zip, but that's probably outside the scope of this tutorial. Anyways, once you open the zip archive kind of thing, you'll have two different things, one of which is an image, one of which is a .lib file. The .lib is the one you want, that's the library. Extract that somewhere on your computer where you want it. I'll put it in my downloads because I don't really care about it too much right now. I'll replace it because I already have it there. And then what you have to do then to get the chip loaded in is if you go to up here to Preferences, there's the second option here that says Manage Symbol Libraries. If you click on Manage Symbol Libraries, you can get a big list of these global libraries. You can see that I already have all of these installed. If you did not have it already installed, for example, or if you wanted to add it to just this specific project, you could go to the project-specific libraries. Press this little folder thing down here. It's Browse. If you roll over, it says Add Existing Library to Table. So if you click on that, then you navigate to where it is on your computer. So mine was in Downloads. Then you can see we've added this microchip library. Its path is already there automatically. And then, after that, hopefully, pressing the A button should let you find this schematic. I'll get rid of that since I don't need it in my project specific, and I already have it installed here globally. But that is the general process there. Philip said he found it, thanks. Is that meaning finding this chip? So have you gotten, I guess, to that stage? Excellent. Fantastic. Cool. Is anyone else having troubles finding the chip and would like some help now? Otherwise, we may vibe onwards. Okay, cool. I will assume that means that everyone has either found the chip or will be catching up as we go along. If you do have any questions or get stuck along the way, feel free to interrupt with a question. Questions are excellent. Nice. So here we are. Here's our chip. We put it on the board. I'll catch up later. My computer isn't so happy. Entirely understandable. No worries. Sounds good. Yeah, this will all be recorded and I'll put up that tonight. Awesome. Well, if you have been able to track down the chip and open it here, this is our little microprocessor. You can see these pins here are labeled. Most of them, I suppose, perhaps quite cryptically, except VDD is the typical symbol for a input voltage. So that's your voltage. I think it's drain usually. And that is where you supply power to the chip. So here that would be anything between 1.6 and 3.3 volts. Or sorry, 3.6 volts. So it's a 3.3 volt logic chip. And down here is the ground pin. You just connect that to ground. So those are the power ones, pretty obvious. These ones on this side are just a set of GPIO pins for different operations, so those we can program what they do. And then over here are some special GPIO pins. They can also just be used for GPIO, like these ones down here we'll be using for that. But these ones here, the SW clock and SWDIO, stand for single wire debugging. And you may notice there are 2 wires. Don't worry, there'll be up to 5 wires later, so it's not really single wire, but it's called single wire debugging because it's just this one pin here that is used for data. So this is how you'd actually program the chip. And this clock pin just kind of periodically goes high voltage, low voltage, high voltage, low voltage. So it can keep track of time as it goes along. And then up here, this is a reset button. You may have seen this before if you've looked at schematics, but when you see a pin or a label that has a solid bar above it, that means it's an active low, which means this will reset the chip if you put 0 volts on this pin. So to prevent it from being reset, we'll actually need to pull it up to 3.3 volts. All the other pins, usually, a high voltage is a on and a low voltage is an off. But whenever they have this bar, that means it's inverted. So a low voltage of 0 would turn on the reset, and that would reset the chip, so turn it off, like reboot it kind of thing. Excellent. So those pins explained. Now let's actually connect it to some things. Once we're here, we probably want to power the chip. So when you're powering microcontrollers like this, it's good practice to use things called decoupling capacitors. Well, I have a link, so I might as well show you a little bit about it. It's a much more advanced link than we will need to go into today at all. But it's talking about decoupling. The main point of decoupling is, in the real world, there's a lot of electromagnetic radiation, and what happens when that hits a conductor, like your wires, or even just the PCB board itself, it gets turned back into electricity, back into electrical currents, and that can create noise. And this noise can sometimes interfere with the performance of these very delicate, like, integrated microcontrollers, so that might sometimes give this very strange behavior. So it's usually advisable to use some sort of capacitor network. So let's see if they gave me a diagram. So let's talk about blah, 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 non-ideal capacitors. They're showing some resonance frequencies dropping down. Yeah, something maybe like this. This is a combination of different things, but you'll often have these capacitors here that are pulled to ground next to the power inputs. You might be wondering why you're connecting power directly to ground, but you're doing this through a capacitor. So remember, capacitors are like almost like rechargeable batteries, kinda, in that you can fill them up and then drain them of electrical charge. But they have a max capacity. They're not like direct wires, which is why this symbol has a break in it here. So it's not going to just run all of your power straight into ground, because it can't do that. Instead, it will just charge this capacitor. And what that does is when this power here fluctuates, say your power temporarily drops a little bit or temporarily spikes a little bit, this capacitor here will buffer that a little bit. So if this power goes a bit too low, some charge will flow out of this capacitor and into the circuit, so that it maintains a stable input power. And if the opposite happens, then it will draw away some of that extra power and store it for later use. So that's the main idea behind these things. You can read a whole bunch about it. If you do engineering, you'll probably have seen this before, like the resonant frequency calculation for things. It's a complex topic, but I've included a pretty thorough thing if you're really, really curious. The good news for you is, if you don't care about it, you don't really need to understand it terribly in detail. The only really important thing is that if you see capacitors and they are near the power input of a chip like this, a microcontroller, that's what they're there for. They're just there to stabilize the power. You can even run these things without those capacitors lots of the time. It's just sometimes you get some weird behavior depending on your environment. So they're good practice, they're not essential. But it's still like very, very good practice, so we'll be including one today. Awesome. For that, we can press our A button again. Oh, just kidding, I need to click back on this window. Then press our A button. And that will whip up our big component list. You can see now our recently used has that chip in there. But what we can do is look for the capacitors. So I'll show you where to find them without searching. You can also just search for them directly in the future. But you see there's a bunch of different categories. Basic things like capacitors, resistors, those are in the device category. So this is just general device things. Then you can scroll down until you see C. That's one of the options. There is also, however, a C small somewhere. Yeah, there we are, which is the exact same thing, just a slightly smaller symbol. I'll show you both of them, actually. I like using the small ones because, well, they're less intimidating. So there's the big one. And if you search C small, small, and then hit enter for that, just a smaller version of the exact same symbol. I'll use the smaller one. You can use whichever one you like best. Time for a new keyboard shortcut. If with your little cursor here you float over a component that you don't like and you press the delete key, it gets destroyed. So you can delete things with delete and place things with A. And now what we probably want to do actually is move this capacitor a little bit. If you roll over and press M for move, then you can move it around, and then you just click your mouse to place it somewhere new. So that's a nice way that you can move things, which is really helpful. Excellent. Then, from there, we probably want to, because the point of decoupling capacitors is usually to connect power to ground, so you're kind of buffering the whole power supply there. So we will then add that next, I think. Well, actually first, let's give this capacitor a value. So these decoupling capacitors, different people will tell you different values. In fact, that big document that I showed a second ago with a whole bunch of graphs in it is talking about, well, since capacitors aren't ideal things, there's like a sweet spot for some of them. For our purposes, we're going to go with a value of 100 nanofarads or 0.1 microfarads. Those are the same value, just different units. That's a pretty common decoupling capacitor value. It doesn't store a whole bunch of charge, but it's just enough to clean up some of the noise that you might get from electromagnetic radiation. So that was a new keyboard shortcut. Didn't explain that one. So if you roll over the thing that says either C small or this will say C if you pick the large capacitor, it's just what the component name is, I think, by default, and you press the E button, E for edit, it lets you edit the value of that field. So here we'll change that to be a label saying the size of our capacitor. So this one we're going to do 100 nanofarads, so nanofarad. N for the nano, F for the farad. There we are. And we can see that up there looking real nice. Oh, also, realize I haven't explained this explicitly yet. I've just been doing it second nature. To get around this, you can middle click drag to move the screen, so like pan the sheet, and mouse wheel or scrolling in and out should, well, zoom in and out. And that zooms in and out wherever you're focused. So even if you can't pan, you can zoom out, put your cursor over what you'd like to focus, and then zoom in, and it'll center it automatically for you, which is really nice. Cool. So there is our capacitor placed, and now we've given it our value of 100 nanofarads, which is excellent. Now all that's left to do is insert some power symbols. So in KiCad, the power symbols are under a separate shortcut than the rest of the components. So the rest of the components, press A, that gives you most of your symbols, but for power symbols in particular, you can press the P key, P for power, and then you can see all the special power signals and power flags. For us, we said that the voltage range of this microcontroller was between 1.6 and 3.6 volts. It's meant to be run with 3.3 volts. Sorry, what did I just say? I might have said that wrong. Yeah, between 3.6 and 1.6, so a pretty big range. We want 3.3, that's the ideal one. So we can then search for that. 3.3. Now you can see, yeah, there's a 3.3. It's also worth noticing, if we go down a little bit, this one here that says 3V3, you might see that when you're creating or, reading schematics. What it means when they put the unit in the middle of two numbers is the same thing as if there's a decimal place. It's just some people prefer to write 3.3 volts, and other people will just shorten that to 3V3. These are absolutely identical. Both of those will supply 3.3 volts of power, and that's what it means to people. It's just sometimes you'll put this V in the middle to shorten things a little bit. You might see the same thing with the resistors, for example. If you have something that's 4.7 kiloohms, then you might see 4K for the kiloohms, and then 7. So you might see 4K7, that means a 4.7 kiloohm resistor. They mean the exact same thing. I'll probably pick the 3.3 because it doesn't require you to know that random bit of knowledge. It's just a bit easier. Yeah, you can see down here it even says alias of 3v3. So identical symbols. This one's just one that says 3.3. So I'll grab that one. Generally, power symbols, you point upwards in a schematic. All of this is arbitrary, whether it's up or down. It'll work the same. But it just makes it easier for people to read. We can also go and press the P key a second time, search G in D for ground, and pick a ground symbol. You can see there's a bunch of different ground symbol possibilities. We'll just use the regular one, and we'll do that. So there we are. There's our capacitor that's connecting our power line to our ground line to help clean up some noise and prevent this from getting too upset. Now, note in real life, these decoupling capacitors need to be as close as possible to this microcontroller so that you don't add more noise on the wires that run between this capacitor that's filtering it and this that's receiving the power. But in your schematic, it doesn't matter where you place things. This has nothing to do with the physical layout yet. That part comes when we're doing PCBs later. Excellent. That's where we've gotten so far. I don't think we've done anything too terrible just yet, but I will create a poll asking how are people doing so far. And we had someone join a little bit late, so if you have any questions about just where we're at, now's a great time to ask so that you don't have to be behind if you are. But basically we've opened KiCad, building a schematic. We put down our main processor chip because we're going to build like a little tiny baby Arduino-ish kind of clone. And then we've also put down a filtering capacitor there. Cool. One person's doing well according to the Discord poll. That's better than 0 people. And if you have any questions, now is an excellent time to ask them. I'll give everyone a second to do that. Cool. Okay. If there aren't any questions, I don't see any at the moment, which is all right, then we'll continue onwards. Cool. Like I said a moment ago, well, yeah, a little while ago, this reset pin here, since it's an active low, we need to pull high, so up to 3.3 volts, to prevent the reset from happening. If that voltage goes low, then the reset becomes active. It resets the chip, which like reboots it, stops whatever program it's running. If we leave this unconnected, what'll happen is random electromagnetic radiation, random interference, random noise will flick this voltage high and low because there's no real capacitance on it. So it'll get randomly flicked high and low, and your chip will reset randomly all of the time and be terrible to use. So we'll need to do what's called a pull-up resistor to keep it steadily pulled up. I think we talked a bit about pull-up and pull-down resistors last semester during our breadboard electronics we did. So we'll do that. There are a couple of ways to connect up schematics in KiCad. You can either do things like this, where you have symbols kind of distant from each other. In fact, we should probably put power to the main chip. Let's do that. M is the move key I talked about a moment ago. That also works for these labels. So I'm going to move this label down here so it's a little bit out of the way. I'll move this one, which is like the identifier, up there. Now, here's a new keyboard shortcut for you. The C key copies things. So if you scroll over something, press C, you will copy it. And then you can go and place that wherever you'd like. So I'm going to place 3.3 volts there at our power input for our board, and ground down at the ground input. So there we are. Now our chip is powered. And the next thing we want to do is do something with this reset key. You can draw wires manually, which I'll show you in a little while, but a nice clean way to do things also is to use labels. There are 3 different types of labels. C doesn't copy for you. Have you clicked on the window and are you hovered over something? I think then C should copy if you press it. But not if you press it over like an empty place, I guess. You have to be hovered over the particular part. And certain that the window's focused, I guess. Yeah, it's a bit weird. It's not like a Control-C, Control-V kind of thing. Although you can do that if you select the whole thing. If you click and drag and select the whole thing. Yeah, it is pretty specific. You have to be pretty hovered over just the right bit as well. Yeah, and you can always zoom in if you're having trouble with it. But okay, that's good to know that it's, I think, behaving for you now, which is good. Cool. I'm going to move actually all of this down, so if you highlight all as a box and just let go, you can move things. So I'm going to move it onto screen there. Yes, yeah, so there are 3 types of labels that you can have. they act a little bit like these power things do, because essentially both these being connected to 3.3 volts means that there's like a wire somehow eventually connecting these two pins. But we don't have to sort that out until we're designing a PCB in a little bit. Three different types of labels. Some labels, which are, you can see over here, there are these three categories. They're a bit small, I'm sure, on the screen. This top one says place net label. Those look like this. So if I click on like that 10 pin and write label, you can see this little label here is around. I can click on that. Does something like that. It doesn't look terribly obvious that that's a label, to be honest, but what this does is just connect to things that are on this actual page of design. So that's good if you want something that just connects on this page. You can have nested schematics. So if you have nested schematics, there are these hierarchical ones, which are these bottom yellow ones over there. And these ones look like this, like that. Those are for connecting up to like other sub-schematics and things. But the ones that we'll be using, because they're both the easiest to use and because they look the nicest, are global labels. That's the one in the middle over here, but what I'll be doing is pressing Control H. So Control H, like, I don't know, you hate designing PCBs, or you love designing PCBs. Either one. I couldn't think of any word except for hate with H, which is probably a bad sign. Anyways, if you press Control H, or H, you'll get to this little dialog. It'll ask you, what do you want the label to be? We'll make one for our reset switch, like that. And then you can go ahead and place it connecting over here. And now we can place this label somewhere else. We can copy it by hovering over it and pressing Control C, put that anywhere. And that means that this will now be connected to whatever I connect to this, which is really convenient. You may also be wondering, well, okay, here I've lost that upper bar. That means it's an active low. Maybe that might be a bad thing to forget. Maybe it'd be good if we kept track of that somehow. Luckily for us, there's a way to do that. If you hover over the reset label and you press E to edit its values, we can see our name here. If we add tildes, like little squiggly lines, to the left and to the right of that word, and then press OK, it goes ahead and turns that into, you want this to be an active low, and it puts the big line over the top of the thing. So that's a way we can keep track of that. I think actually, yeah, we'll keep track of that. Why not? It's good because it shows off that nice little tilde feature, which not too many people know about, so that's a good one. That adds the bar above the whole thing for an active low. It's totally unimportant, by the way, what you name these. You can name this whatever you like, foo, and it will work exactly the same. They're arbitrary. It just means that anything with this same name will be connected to this pin. So yeah, don't stress too much if you don't like this name. Name it whatever makes sense to you. Cool. Nice. With that out of the way, we have our little global label there. That's pretty cute. We'll also, while we're at it, add some labels to these programming pins. So the software, or sorry, this, yeah, it stands for single wire debug. That's what SWD stands for. SWD-IO is input and output. So this is the input-output debug data. This is the clock. We'll just create labels with those exact same names and connect them here. So Control H for global label again. SWCLK for that one. Then I can do C to copy, drag it down there, and then E to edit, change that to Swidio. There we are. SWDIO. Beautiful. That's all connected up with labels, so that looks good. Nice. How are people vibing along so far? I think probably not too bad. How are people feeling my labels? Okay. Yeah, there we are. Again, I got a response for preempting my poll. Well done. Cool. In that case, then, let's move on to the next thing to do, which I think will be to actually create the reset switch and pull up, which will be helpful. Right, so remember how I said this resets an active low, so if that ever drops to 0 volts, it will turn off our processor, which kind of sucks to happen randomly. So most of the time, we want to prevent that from happening by pulling it up. And we can pull it up by using A to add a component. We'll go R for resistor. Go ahead and grab a resistor. I'll put that over here just so it's next to my other power thing. Remember, we want this to be a pull-up. I'll copy the 3.3 volts over, just like that. Instead of copying ground over here, though, I want to copy the reset label. So there we are. Here's a useful shortcut that I didn't get the chance to explain yet. If you press R while something is like being moved around, or even if you're just hovering over it, it rotates it. So I can rotate that there. And you can even rotate things after they've been placed without clicking. So if if I hover over this resistor, press R, I can rotate that as well. For Shinsuke, if you missed that little bit there, R rotates things. Very exciting. Oops. Also, sometimes you might see clarify selection. If, for example, I press reset or the rotate key over this, I'm hovering over the resistor and the reset label. It doesn't know what I want to rotate. So I can just clarify by saying, okay, I would like to rotate the global label, actually. So if you ever get that, that's how you disambiguate. Lovely. So there we are. This will pull our reset up, so our chip won't randomly reset by default. This also, however, doesn't give us any way to reset it if we'd like to reset it. So we'll need to design a way to do that in just a moment. We should also give this resistor a value, so we can enter that value field there. I'm going to go with 10 kilo ohms. That's a pretty common pull-up resistor value. These resistor values can be quite large because the point of a pull-up resistor isn't actually to have much current flow through it. You just need a very, very small amount of current to flow through just so it keeps this reset pin pinned at 3.3 volts. But this should be big enough so that you can connect this reset pin to ground through a button, and it pulls it down to ground faster than this can pull up, I guess. So you need to have more current that can empty out to ground than flow in through this. That'll make more sense now, because that's the next thing we're doing. So if I go here, let's build our reset button in this little empty space. I can press the A key and look for a switch. So if I recall correctly, I think it's under devices that switches are. I'm not actually entirely certain. Well, worst case scenario, we can just search for a switch. I'll try and find the category for you, though. The category is switches. There should be something called switches. There is somewhere, I'm sure. Yeah, switch. There we are. Ages away. Again, you can search for these things. That's probably the much easier way to do what I just did. I just wanted to show you there is a dedicated category for it. So if you can go ahead and look at switches, there's a whole bunch of different wild things. Like, look at those. These are rotatey switches that'll give you outputs if you rotate them to different things, like dial switches. That's really cool. I like that a lot. Dip switches, those are the tiny ones with a little little levers you can kind of flick. What we really want, though, is just a single push button. That one's called SW push, I believe. There we are. So that's just a normally open push button. When you push it down, it'll connect these two pins to each other. That's all that one does. So there we are. There's our button. That'll be our reset button. So I can rename it, hover over this field here, press E, and then call it reset. Excellent. So that's our reset switch. Now what we want to do when we do want to reset this, because it's an active low, is we just want to take this reset pin down to 0 volts. Doing that is rather easy. All we need to do is copy this label here with C, hover over it and press C. There we are, we copied the label. Here's our reset switch, and we want to connect it to ground. We could do that. That works. It looks a bit cluttered maybe, so this is a good opportunity to show off the wire tool. If we want to give it a bit of space. See, I mean, depending on your taste, that either looks cluttered or nice. I actually almost like that, so I might go back to that in a second. But you can place it a distance away. And if you ever want to connect components that are, well, not directly touching each other, if you want some space between them. Finally, our last keyboard shortcut, I think, just a letter, is W, W for wire. You hover over where you want the wire to start, press W, drag your mouse, you can see it will automatically build like a little 90-degree angle thing for you. If you click, it will fix that point, and then you can go kind of from there. Well, it'll fix that point a little bit, like that kind of thing. So fixing the points, you can draw stuff like that, which is ridiculous and totally unnecessary. Escape, I think, to cancel. Yep. So if I go here, press W to start, just go down there, and then click where I want it to end. There you are. It's connected those two symbols together, and they're electrically connected now, which is really nice in the schematic. I have decided I like the original thing better, so goodbye, wire. of just moving that and connecting that there. Both of those are, again, entirely identical. It's just a matter of taste. Some people use wires to connect the entire thing instead of using these labels at all, but I think the labels are probably clearer than doing that. Cool. There's the reset switch. I actually might put that over more on the reset switch side, so you can click and hold or click and drag to highlight it, and then you can move it wherever you'd like. I'm going to move it over there, next to the reset switch, kind of, sort of. I'll do the same with this resistor for the reset switch. Excellent. Cool. From there, I think it's about time that we start adding some GPIO pins, I believe. Before that, though, no development board is complete without an Arduino. You need to write your little blink program that blinks your LED on and off. Yes, yeah. So for our blinking LED, then, we want to pick one of these inputs, I guess, to connect it to, and just connect it to ground through a resistor, of course, because LEDs always need resistors to limit the current so they don't get damaged. So step one of that is finding an LED. If we press our A key and search for LED, you can see there is one of them. That's a perfectly valid symbol. There's also, if for some reason you'd like your LED filled, which I think does look a bit nicer, you can go down to LED Alt, which is the exact same thing, just an alternative shape for it. So I'm going to click on that. There's our LED Alt. Go ahead and place that. And then what we want to do is build our little LED circuit. So let's say connect this one up here, O2, so the second pin, or I guess this is kind of like our first totally unassigned GPIO pin. Let's make that one the one connected to the LED. So remember, global labels is Control H. I'll call it LED. Here it is. It's the wrong way around, so I press R twice to rotate it. And then go ahead and click there to connect it. I'll also rotate this LED. That was too many times. I wonder, does Shift R go backwards? Nope, it does not. Does Control R go backwards? No, it does not. So you could just rotate things all the way around, I guess. Nice. That looks good to me. I'll move that down a little bit so it's less close to all of this up here, which can move up even. There we are. Then we want to copy our LED label. That's going to be providing power, so that's the positive side of our LED. That positive side is the side that's got like the little triangle on it, and the minus side, the negative side, is this, well, minus sign part here. There are a couple of different ways to remember that. I like to remember just the minus is the negative side of the schematic. Alternatively, this triangle could look like an A, because that's the anode, but then that also requires you to remember that the anode is the positive side. Anyways, point is, ground, you connect to the side with the flat line. Whatever power or input, that's on the other side. Cool. We can't fit our resistor, so I'll go ahead and add a resistor with A, go down to my R with my arrow keys and press enter on my recently used stuff. Rotate it. I'll have it like this, actually, and now I'll put it in a line. Why not? Like that, and then we'll have ground on the other side of that. Oops, that was a move, not a copy. That's my bad. Press C to copy, of course. There. This one we can wire up with wires, because otherwise it would look a little cluttered. So W to start a wire, so hover there. W, click where you want it to finish. W, click where you want it to finish. There we are, wired up. Awesome, and there's our little LED circuit. So now we can tell our microcontroller, set pin 2, or 13, I guess, depending on how you're counting, to high, and that will turn on our little LED here. Of course, we need to give this resistor a value. That's my bad. Resistor values vary wildly. Depends on the LED, how much current you want to go through it. I think we actually did some calculations for that back in our electronics session last semester, but we'll just roll with something simple for now. 1 kilo ohm, so it's pretty big, so it'll be not the brightest LED in the world, but that's fine. We just need to turn on and off. And these LEDs will probably be very, very tiny, since this whole board is going to be very, very tiny. So that looks good. Let's see, what might we want to do next? I think we can add a programming header. Yeah, so to program this board, we can't program it with at least this particular microchip. can't be programmed directly with a USB connection like lots of Arduinos can. So instead, you need to have a specific programmer that's capable of talking the SWD protocol or whatever, and you need to connect it to the clock line, to this line, to power, to ground, and also to reset. So that's 5 different wires that we'll need to all break out in some sort of connector. So what we can do for that, a very standard shape of connector is a 2x3. So you'll notice that, of course, is 6 pins. So that's 1 more than we actually need. That's fine. You can leave things unconnected in KiCad, no problem. So yeah, let's do that. If we go to a new space over here, maybe will be a good place to write or to build our little programmer header. We can press A, and we want to look for a connector. So con is a way you can find those. You give an underscore, and then you give the shape of the connector you're looking for. I'm looking for a 2, so 0, 2, and then by, so X, 0, 3 connector. These are numbered different ways. The difference between these is very, very subtle. If I zoom in here a little bit, you might be able to see it. So these pins are named counterclockwise, starting from this top right. So it's 1, 2, 3, 4, 5, 6. These pin numbers are, in our case, totally unimportant, but do be aware there are odd even numbered things, which go a bit like this, where you have 1, 2 across that way, then 3, 4, then 5, 6. This is more like the order that you'd read English text in or something. So I'm going to go with that one, probably. And then we can just place that connector, say, up here. And voila, we are done. I'll rename this long, gross thing to be more useful, so we remember what it is. These names are unimportant for us. They're just, well, unimportant for the program, but important to us, so we remember what things do, I guess. So roll over that big, long, odd, even thing, press E, and then we can change it to something like programming or program header. I feel like we can shorten that to just SWD. So that's the single wire debug thing that this is programmed with. And then we'll do underscore program as PGM. There we are. There's our little programmer header for single wire debug. Now we'll have to actually connect that up to things on this microcontroller, or to power and stuff. So how you connect up this can vary wildly depending on what programmer you're using. And by programmer, actually, at this point, in case you haven't dealt with things like this before, so if your only experience with microcontrollers has been like Arduinos that are, well, easy to use, be aware there are also things that aren't as easy to use. So let me find like a JTAG programmer. Yes, when I say programmer, I mean an actual physical device, not like you, the programmer. Because basically, to get these chip programmed, to put stuff into its memory, to get it all set up properly, it's a very specific language, almost, that it needs to talk over these 2 wires. But to speak that language, your computer doesn't speak it directly, that's for sure. You need a little helper device that will translate your USB connection, usually that you have to your computer, to something that you can connect to the microcontroller. So like here's actually a really good example of one. I hope this isn't in German. It's entirely in German, of course it is. Oh, that doesn't help us. It's from SparkFun, but that's fine. If I zoom in on this, you can see it a bit better. Vergroßen bitte. There we are. So you can see here, it's got on the left side that USB connection. It has its own chip and logic and stuff going on there. That translates it to this other language that flows out over this header, and then you can connect this header to basically the header that you want to program on the board via a ribbon cable like one of these. So that's the general idea of how you can use a physical programmer. That's how this board would need to be programmed. If we want to make a fancier one, we could pick a chip that has USB programming support, or build in essentially that programmer logic onto our board. But to keep things small, we won't be doing that. We'll just be using a little external programmer, if you will. Cool. Point is, depending on which one of those external programmers you are using, these different pins will mean different things. So it's very important that you check that. In this case, we'll just be going with the layout that the original tutorial used, because that one is a common one for JTAG debuggers, I believe. But just be aware, the exact layout of this programming header is definitely different from board to board. Nice. Okay. So let's connect things up here then in the nice easy way, which is to grab the I/O thing. So copy, remember, roll over and press C. That'll be our first thing. Our second pin will be the clock. Then we'll have the reset line on the bottom. Now you'll notice, because I put that bar on the reset earlier to show that's an active low, it's kind of overlapping that label. If you think that's ugly, it kind of is. We can move it down, over, and then just do a wire connection with W. That's purely aesthetic. They mean identical things. But even when things aren't essential, it's nice to try and make them look nice for other people to look at. Same with coding. There's a million ways to solve a problem, but sometimes there are prettier ways to do it. So up to your own discretion. Additionally, this program header needs the power connections, so it can provide power directly to our board when it's programming it. So we can do 3.3 volts and ground. I'm keeping those arrows vertical just for the sake of the convention. Oopsie daisy, didn't mean to do that. Accidentally duplicated it. Then we'll wire this up with W, click where we want it to end, W, click where we want it to end. There we are. Everything there set up. That's actually all the wires we need for our programming header. This 4, you'll notice, is unconnected, but we don't ever want to connect it. So there's a way that you can mark that in KiCad with a little no connect flag. The keyboard shortcut is roll over what you would like to mark as non-connected and press Q. Q as in a quail, I guess. That's a very specific word to come to mind. Welcome to Brooks's live, word association games. Anyways, if you hover over the thing and you press Q, that'll mark it with this blue X. That'll say, don't connect anything here. You can also see in this right bar, it's an option, so you can click on that manually if you'd like as well. Cool, there we are. That's connected. Program header is all set up. Now, I think what we want to do, all that's really left to do, is to mark all of these GPIO pins. Give those a place to actually connect to the outside world. So we'll be adding yet another connector, another header like this, and then that's what we'll connect all the rest of these wires to, I think. I'm just shuffling things around to try and desperately make them look pretty, but no matter what I do, schematics look like schematics. Excellent. Cool. All right, so let's drop in some connectors then. Yeah, I'll put those down here, I guess. So I'll go ahead and press A. This time we have, well, first we'll take a look at it. 1, 2, 3, 4, 5, 6, 7, 8 pins left to be used. So we can do 2 1x4 headers, I think. And that's something that you like put in a breadboard, which would be nice. So con 1, and then X for by 2. There we are. Sorry, by 4. Don't know what I'm talking about. There we are. So there's our nice connector. I will place that here. I'll rearrange by hovering and pressing M to move that label up to the top, this thing down here to the bottom. In fact, I'll rename this by hovering and pressing E to GPIO A. A because there'll be an A and a B, there'll be 2 of these. Go ahead and put that there. That looks good to me. Now what we can do is copy that part, put it over here, make this one GPIO B. If you'd like a bit more visual clarity as well, that these two are different, cool little tip here. You can hover over this B, press E for edit, and you can get a whole bunch of different values, but what we're interested in here is aspect mirror around Y axis, and that will mirror it vertically. Go ahead and press OK. There you are, flipped around, nice and beautiful. You may be wondering, what's the difference in mirroring and rotating something? Well, that's just, they're fundamentally different, like geometrically. I'm sure group theory has plenty of things to say about that, but for those of you who could not care less about that, which is probably the proper response, if you rotate it, the pins will be numbered the opposite way, and also, well, the labels will be flipped upside down. You can, of course, move the labels individually if you'd like. So like say, hello, Mr. Label, you go up there, you go down there, kind of thing. But your pin numbers will still be wrong. You can change them by changing the whole symbol, but at that point, it's really probably not worth the effort. So flipping is different from rotating subtly, but the pin numbers are the real dead giveaway there. And this is, again, purely aesthetic. There's absolutely nothing wrong with it being this way. That's an entirely valid solution as well. Again, just so you can tell them apart aesthetically, and it's a neat feature to be aware of. Lovely. So there's our GPIO A and B, and now we just need to connect those up, and we'll be using global labels directly to our microcontroller. Yeah, so there's a lot of different ways to metaphorically skin this cat. No cats were harmed in the making of this tutorial, but metaphorically, there are lots of ways to do this. I'll press Control H and do GPIO and name this one 1. So _1. So there's our first one, and I'll put that on that pen there. Now, here is where you could, and I'll do this the first time, hover over this label, press C to copy it, drag it down here, hover over it again, press E to edit it, go to the last digit, change it up by 1, press Enter, there you are. However, I have today discovered a super neat little trick. It's decently hidden. This tutorial doesn't talk about it, but I managed to track it down, which is really cool. If you have a bunch of things in a row like this, so you know how all of these, basically what I need to be doing is 3, 4, 5, 6, 7, and 8, all the way down in a line, which would be really repetitive to do. If instead, I just go up here once, and insert my global label with Control H, do our GPIO 3 in this case, rotate it twice, oopsie, rotate it twice, and then place it. You can now press, if you have it on your keyboard, the Insert key, sometimes abbreviated as INS, and that will insert a next label for you. And you can see it's 1 down, it's connected to the proper pin, and it's automatically increased the label number by 1. And so you can just keep doing that until it's done, which is fantastic. And it also like goes past when it's done, because it doesn't, it's not terribly smart, to be honest. But it is a really useful feature, and if you do go too far, you can use Control Z, just like anything else, to undo. And there you are, automatically got all those. Again, of course, the alternative, if you can't find your insert key or something, you can go and copy them manually and rename them. But yes, I agree, Shinsuke. Wow, indeed. I discovered that about 45 minutes ago today. It's pretty cool. It's even cooler now, because basically what we need to do is do the same thing over here. So I'm going to go ahead and copy this first one. I think this will work. Place that, and then do insert. Yep, and it'll do 2, 3, 4. And I'll go over here, and I'll copy 5, which will be the first one on the other side, with C. And then insert, insert, insert. And there we are, we're all the way up to 8. Magic! It's so much faster that way, it's really cool. So there's your spicy secret tip for today. And just like that, I actually think that these GPIs are all wired up. The point of these is just to make these will be like little pins that stick out of our circuit board that you can connect like wires to. That just is much easier than connecting directly to the super tiny little solder pads that this chip will have going on. Makes it like an Arduino or a Raspberry Pi. Cool. I think that is just about everything there. This is the basic schematic done. I will show you now some cool things. First of all, you'll notice you have these different little labels here. You have the R's for resistors, SW for switches, U is the thing for boards like this. And I'll jump to that question in just a moment, Shinsuke. D for diodes, like this LED here. J for jumpers or connectors. But all of them have question marks after them, so they're not actually numbered yet, so they're not actually uniquely identifiable. You could, of course, go along and say, okay, hello, Mr. Switch. I will hover over you, press E, and you will be switch 1. Lovely. But doing that with everything all the time can probably get old. So built into KiCad is a nice way of doing that all automatically. Up here, to the right of the, or sorry, to the left of the ladybug, you'll have something that if you hover it says annotate schematic symbols. Alternatively, if you go to tools, I believe, yeah, if you go to tools and then you scroll down to annotate schematic, that pops up a little window. Default options are fine. You can press the annotate button and then close, and voila, just like that. All of these now have unique numbers that count up. So this is resistor 1 over here, this is resistor 2 over here, this is capacitor 1, this is connector 3 because connectors 1 and 2 are down here, and then here's microchip 1, it's our only microchip. Oh wow, that's just connected a dot for me. It's probably U because U is sometimes the symbol for micro when you don't have a mu available, and it's a microchip. Go figure. now we know. Anyway, so that's a nice way that you can mark all of these with unique labels. Now I will answer Shunsuke's question. If we use a development board like Arduino, everything here is all inside, but this way we can make custom and efficient one, right? Yes. So basically what we're doing right now is, designing our own Arduino with this, smaller processor on it. That's the whole point of development boards like Arduinos, is they do all this bit for us. They break out these pins, they do all this custom stuff. But if you want to build one PCB that has a processor on it, but instead of, having pins to connect random things to like an Arduino, your thing just directly connects. It's on one board and it directly connects to, say, all of your amplification machinery for your EMG data and all of your filters, and just all directly connects on a single PCB. This is how you could design it, in fact, what I did when I was on the Avalon team for making the little circuit board for the miniature rover, something that the people there suggested, and I assume their experience, they were fourth-year electrical engineers, they said, lots of the time, if you have something that you want to build, but you could do it with an Arduino, here's your hot tip. You can go to an Arduino, so say like Arduino Micro if you want something really tiny, or is it Mini? Sorry, I'm thinking Mini. And then Schematic, as Google has so helpfully suggested for us. And then, et voila, there's a schematic for an Arduino Micro, because they're all open source. Well, I say there's the schematic, and it takes me to a place that doesn't have the schematic. Very helpful. Well, here's a really low-resolution version of the schematic. You can find it better in other places. But you might notice some similarities. Oh, well done, Brooks. I managed to zoom all of that right back out in the end. But you might notice some similarities. For example, here is the big square. That's the microcontroller. I can't read any of those pins either. Don't worry. It's a really low-resolution image. But they've automatically connected over here, for example, a power regulator. Yeah, I think this is a power regulator over here in the top left. So that's what's allows you to plug in like 5 volts, and it converts that 5 volts down to 3.3, which is safe for the microcontroller or something. Here's all of their input and output pins that they've labeled up with global labels, you can see, just like we've done. They've got their capacitors over here. Here's their reset system, where their reset is connected down here to a ground through this switch, and then pulled up by default through this big resistor. So yeah, a common approach when you're designing these things is if there's an Arduino that's similar to the custom board that you want to make, you can borrow their schematics, because it's open source hardware. And all of this stuff is already in schematic form for you. You can just edit it to your needs and then print your own circuit boards. So yes, it was a very long, long way to answer that question. Sorry about that. But yes, if you have a development board, it'll already have all of this built into it. We're building our own development board is the idea here. Yes, and you can build custom ones. Or make it not even a development board, just a custom thing for a custom application. But yeah, awesome. Hopefully that answers that question. Cool. Excellent. Yeah. Here's a good place to save. I think I forgot to do that most of the time. Save button's obviously in the top left here, or under File, or Control S. It's good to always develop a Control S habit in most programs. And one last thing I'll show off is this little ladybug thing here is a debugger, very cute, or an electrical rules check, sometimes called an ERC. In fact, what I'll do is I'll get rid of this do not connect mark there. So I'll get rid of the no connect, and then I'll run this. Go ahead and run the ERC. Note you'll need to have done that automatic annotation beforehand. And it gives us now 3 errors. It says that 2 of our pins are connected to other pins but not driven by other pins. So that's just saying that the power, it doesn't know, there's no actual input power, which, I mean, to be honest, there isn't. We've just said there is 3.3 volts here. We didn't say how it gets there. And it's also said, hey buddy, you haven't connected this pin over here. So if we forgot to connect a pin, this will point it out to us. And we can be like, okay. Well, I either need to connect something to this, or I can do, well, what we had before, mark it with Q as a don't connect, and then if I rerun the rule checker, it doesn't give us that error anymore. So this helps you find out if you've done something silly, like connected power directly to ground, or it catches all sorts of little errors, and it's a really nice sanity check before you move on. So that's up here, electrical rules check is the ladybug, or I think in tools, you know what, maybe it's not there in tools. Somewhere. maybe, but I would use the ladybug, because that's the one where I know where it is. The little ladybug button, perform electrical rules check. So that's a helpful little thing. We'll see in a minute how you can get these power errors to go away, because the next thing to do is actually add power. And I think that's the last thing to do for this development board. Cool. So that is that. Nice. I will do a little poll, asking how people are feeling, and if anyone has any questions, now's an excellent time to ask them. So, people feeling about things so far. There's your poll. In a second, Discord is moving really fast today. There we are. So you can say if you're doing well, or if you're a bit confused or anything. Any specific questions, now is a great time for them. I'll give everyone a second to ask or think about that. And prepare the next bit. Yeah, I'll do that. Okay. Nice. All right. I don't see any immediate questions. People seem to have given some positive reactions, so that's good. So we will head on to the next bit then. Cool. Eagle can do the same. Yes. Yeah. Yes, Eagle can do lots of other things as well. I have never used Eagle, to be honest with you. I've actually only used KiCad, but that is, as Shinsuke has pointed out, a nice alternative thing if for some reason you don't like KiCad a whole bunch. So that's something. Yeah, how do you solve the annotations required? No worries. If you go to, well, basically that just means that probably some of your labels around don't have, like, maybe your R1 is still an R question mark or your J1 is still a J question mark. You can automatically annotate everything by going to Annotate Schematic Symbols. That's the button immediately left of the ladybug. And if you do that, just on the default settings, go ahead and press the Annotate button. And you press that, and that will automatically fill in any missing annotations, I think. That's also something you can find in Tools, and then Annotate Schematic, and then you can press the Annotate button. Hopefully if you do that, and then run your little rule checker, it should work. Fantastic. Cool. Happy to help. Nice. Cool. So, lots of what I've been doing so far, you just had to trust my word on it. That's because I'm partially trusting the word of the original tutorial this was all derived from, but also, when you're designing these sorts of electrical schematics, the source of all truth is the manufacturer's data sheet. Data sheets are simultaneously the most useful thing in designing custom electronics, and also the most terrible thing in the world, because they are massive sometimes. For example, this data sheet here, which I'll zoom in a little bit for you, has everything you need to know about this family of microcontrollers, like the one that we're using. The problem, of course, being this is a 918-page document. This has every single technical detail anyone would ever need to know about this chip, which is really good if you're looking for something specific, but it also makes it a bit hard to sift through if you don't know what you're looking for. So I'll point you, I guess, to the most important bits right off the line here. For example, at the very beginning, you usually have the most relevant information, like the features. So here is a bunch of information about what this chip is capable of. And quite importantly, at the very end, you have our operating voltage. So remember earlier when I said it was 1.6 to 3.6 volts, here's that. It'll tell you it's actually 1.62 to 3.63. So there's your operating voltage. So don't give it more or less than that, or you could burn it out. Block diagrams kind of show what the inside of the chip looks like as a processor. That you probably don't need to deal with, to be honest, very often. Pinout, that's one of the most important ones. So KiCad already knew this for us. It already knew which things were which. But here you can find different potential packages that it's in. So here's a 14-pin version. Here's a 20-pin version. Here's one that has ball soldering. So this means the connectors are on the bottom of the chip, and you have to have a special heat gun or something to melt little solder balls onto a grid of contacts. Here's a QFN one. So that's quad flat. QFP is quad flat package. That's something similar where it's four-sided and flat. So you can see it comes in a whole bunch of different shapes. So this is where you would figure out the exact shape that you're working with. We're working with one, I think, that is this 14-pin SOIC, if I believe. Yeah, that's the one we're working with, is this top one. So here's the physical connections. You see those are different from the schematic ones, and that'll be relevant in a minute. The other thing that is good to know is sometimes they have like example applications kind of thing. So we'll look at electrical characteristics, I think, and that has inside of it, if we scroll down, yes, some example diagrams. So that's a measurement schematic. That's not what we're interested in. Yeah, so this has a whole bunch of info about the electronics. There was a nice little schematic there. Is that something I'm concerned about? That's ADC inputs, I guess. That's what those might look like. You want a resistor on the outside. Unfortunately, well, actually, does it have subcategories over here? Oh, it does. That's what I was looking for. Sorry. Yeah, power consumption, I think, and peripheral power consumption. I think that's where we want to kind of be. Packaging a schematic checklist. Sorry, being silly. The thing down here, that's 36, says schematic checklist. This is, as it sounds, like for us, a checklist for people making schematics. So this here, for example, shows here's how you should connect up your power with these different decoupling capacitors. I have not actually followed these recommendations exactly, but I have done the 100 nanofarad one very close by. If you wanted, we could farther away put a larger filtering capacitor, but this is the close to device side. So these are the ones that need to be really close to coupling capacitor to those pins, the power inputs in the ground. You can also see that's for analog reference voltages, which I'm not too fussed about. Reset schematic, here's our reset circuit. This one, and the tutorial acknowledges this as well, has used the optional pull-up resistor, because there's actually an internal pull-up resistor, which is cool as well. So this one's added an optional external one to make it a little more unlikely that it'll be accidentally triggered. It is a good point to point out, though. Having an internal pull-up resistor, like this chip does, is the exception, not the rule, which is why it's good to get in the habit of adding pull-up resistors, because sometimes if it doesn't have an internal one, the chip will behave entirely erratically, be unusable. And they've also suggested here that you could add a little series resistor with a switch, so that, for example, when your decoupling capacitor basically doesn't instantly discharge like when this switch is flipped. So it slows it down, it limits some current. We haven't included that either. The tutorial's gone ahead and made this thing without it and acknowledged that it doesn't have that. The chip works all right. But if you're really concerned about electrical safety and making sure that none of your components ever get worn out, then it's good to follow the recommendations that they give in their checklist here. So I would add that extra, little resistor there. Awesome, and it gives you stuff on how to do like with clock oscillators and all sorts of things. So yeah, this is a really useful section as well. So schematic checklist section, that's a good section to look at, as well as the pinout sections and the feature sections. So those are like your general highlights, I guess. And if you're looking for something else in particular, well, it'll probably be one of the many sections in between. Nice. Yeah, so luckily we're working with things that we already, well, via the knowledge of the tutorial and me, we already know how to deal with. If you're working with a chip you've never seen before, the datasheet is your best friend. So there we are. There's that. Moral of the story is, we need to power this with something between 1.6 and 3.6 volts. 3.3 was fine. We need a way to actually get to that. So this particular board was designed to be battery powered. So let's add battery power. So if I go over here, it's not actually a ton of room there. So I'm going to highlight this whole thing, move it a bit to the right, and put battery power over here on the left side, just for organization's sake. Over here then, we will add a connector to connect our battery to. So batteries are just going to have a power and ground connector usually. Sometimes I can have more. So I can go get a 1x2 connector. Here's where I need my 1x2 connector. So con and then 0.1 by 0.2. There's our generic 1x2 connector. Beautiful. Plop that down somewhere. I'll move these labels so that's on top. So this one's on the bottom. I'll rename it to be battery. Move it there. Nice, looks good. I'll zoom in a little bit. And move over this way. Put that up there. Excellent. So there's our battery input, but batteries probably will not be exactly 3.3 volts. In fact, that's quite rare for them to be exactly the power you need. And even then, power the voltage, kind of decreases on a battery sometimes as they get drained, which is Obviously not something we want. So to make sure that our power is somewhat consistent, we can use a power regulator. Bunch of different types of them. Just depends on what you want to do, essentially. Like buck converters are crazy ones that can move voltages up and down, and those rely on having big capacitors and inductors that can store the charge, and they do all sorts of, they do like a fast switching thing. But the ones that you'll probably see the most often, especially on these development boards and stuff like this, are called low dropout linear regulators. The low dropout means that they don't lose a bunch of voltage. So say if you put in 3.3 voltages, sorry, if you put in 3.3 volts, out the other end will come something only very, very slightly smaller. It doesn't waste a lot of power is what the low dropout means, so you probably get like 3 something volts out of it. But the linear regulator means that any additional voltage, any power it doesn't need, it kind of dissipates away as heat. So they're not terribly efficient, but when you have a small difference, like say our battery, well, okay, let's find out together. LiPo battery voltages. Well, not a voltage tester, just what's the voltage of a normal lithium polymer battery. Okay, it depends on the chemistry, varies between 4.2 volts and 3.7 volts. So when you have a difference that small, we're just moving from 4.2 at most down to 3.3. Linear regulators are exactly what you want. They're really tiny, and they get the job done. So for us, then, we'll pick a linear regulator. Ooh, I need to remember which one I was using. Most of them are quite similar, so I'm going to do add here. There's a whole section for linear regulators, actually. If you go down to the L's, you can see them. I won't look through all of them. I'll search for the one that I know I'm looking for. I just, again, want to show that a category does exist for it. Of course, I've already gone past it. LMNOP, linear regulators. You know, maybe I lied to you, and maybe there's not one. Let's see what category these come out in. Regulator linear, of course. They've switched the order of the words for me. Yeah, thank you, Philip. You found it. Yes, yeah. It's just regular linear. Regulator linear. They've just switched the words on you. So there are a bunch of different ones, obviously. The particular one we're going to be using here in this tutorial is the APE 8865NR. And then you can see there's a whole bunch of different families here. In fact, I'll make this window slightly larger so you can see a bit more detail about them. It says fixed output 1.2 volts, 1.5 volts, 1.6 volts. So you can see this third to last number here is the one that gives the power. So 1.2 is 12, 1.5 is 15. So we can guess 3.3 is probably 33. So if we go up here, 33, there we are. Click on that. You can see it's a low dropout voltage regulator with a fixed output of 3.3 volts. It's in this nice little 3-pin package here called SOT23, which is what we want. And it has a fixed output of 3.3 volts. Just what we're looking for. Excellent. So I'll go ahead and grab that and put that down there. Cool. These often need some external circuitry. So I have the data sheet for this regulator as well. Oh, well, that's where I could have found what it was called, was by looking at my data sheet that I saved for it. It's a whole family of regulators here, so you can see that doesn't have like the particular number. But again, this data sheet, important things to look at. First couple of pages that have like the feature stuff, for example, relevant for us are the features of it has a low dropout voltage. That's good to know. And here's a typical application circuit. They put that right at the beginning, so we're going to be using that in just a second, which is fantastic. There you can see those YY bits. That stands for the different voltage options that you can have. So that's what we figured out a second ago, where 12 is 1.2, 15 is 1.5. What other information I was looking for? Here we are. Pin configuration. That's the last bit of relevant information here for us. And here we have, you can see versions that have 5 pins, but also the one that we had, which was a SOT23, which is just like this. It has 3 pins, of which those you just have the voltage input, voltage output, and the ground. So the voltage input is something higher than 3.3 volts. Voltage output is exactly 3.3 volts. Ground is where you connect ground. But these things often like external capacitors to help them do their job, keep things noise-free. So it wants a capacitor, it looks like, on both the input and the output of the voltage regulator. And we don't have these shutdown and BP pins on our version. We just have in, out, and ground. So we just need to worry about the top part of the schematic. So for that, let's go pop back and add our capacitors. So here we are. Here's our chip. First, let's copy ground. So if I zoom out a little bit, hover over that, press C, copy over our ground. In fact, we want to do that 2 more times, just through a capacitor. So I'll do that there, and then also go over to here, which is almost symmetrical if you squint hard enough. And we want to add a capacitor. I'll press A to add a capacitor. Just search for C_small. That's the small capacitors. Small as in the schematic itself, like the actual values of the capacitors can be whatever you'd like. Copy that over here. I'll move these words to the opposite side. Clarify the selection to be that field value there. Doop and doop. And I'm moving things with M, of course. Then I'll wire it up with W. And wire it again. Once you already have the wiring tool activated with W, by the way, you can just click where you want to start and then click again where you want to end. I'll rename the chip a little bit. Well, actually, that's probably not a good idea. Yeah, you just want to keep it as what it is, so that way you know when you're building the actual thing which thing you need to buy. Excellent. Now, the last thing is this voltage input actually needs an input voltage here. So we'll add a new power connector. So if we go to power, we can look for the BAT symbol. It's for a battery. So that's plus BATT, battery there. That is going to be what's connected on this side. And then on the other side, we'll have our 3.3 volts. And that's because that's the output voltage. So I'll try and line that up roughly with that. Close enough. And then I can just use W to wire that up. Oops, that was my bad. Click there, and when you click on someplace where a wire already is, so where like 3 wires connect, you'll get this green dot. That means it's a node. That means the wires going vertically and horizontally are connected at that spot. So I'll go ahead and do that here as well. It automatically adds those nodes for you. And that looks like the regulator done, which is pretty nice. That was easy enough. And we'll move that slightly over. And same with this battery connector. We need to actually now put the ground and input things on this battery connector. So take ground. Well, don't take ground. Copy it even. So copy it with C. Put that there. And we want the input here. Our input power from the battery, remember, is plus BAT. So that's the symbol we want to copy over here. There we are. I'll wire it up. Click and click. Beautiful. Now that is powered, which is really nice. So I think that's about the extent of what the tutorial itself does, but I will take a quick detour to talk about how you can get the that rule checker to not complain about, well, that error it was complaining about a second ago. So we'll run it first. So if we go to our little ladybug, run it again. Oh, of course, annotation's missing. So first, left the ladybug, annotate schematic signals. Just annotate with the default settings. That keeps all the existing annotations exactly the same and has added new ones. So this is our new 4th connector, J4, 2nd capacitor, 3rd capacitor, things like that. 2nd microchip now. Now we go and press our rule checker, run the rule checker. It's giving us 3 errors. Uh-oh. So we can take a look at it. First of all, there's a no connection somewhere. So if I click on that, oh. Thanks, rule checker, for catching that. I didn't even know I did that. That was entirely unintentional. I, at some point, instead of copying, stole what reset was connecting to. That was 3.3 volts, I think, because that was the pull-up resistor. So I'll copy that back there. See? Rule checker catches real errors when I'm doing dumb things. So there we are. No more unconnected things, at least. Now it's just saying that it can't figure out what power connections are doing here. I can link a really good article that explains this in detail, why this problem happens. But essentially, it's because, well, let's see. Go ahead and run so I can look at where those errors are. Well, okay, it's complaining about those being there and here. So it's complaining about ground, it looks like, and BAT as being not fully powered. Well, it doesn't really know where the power comes from. So if you think about it again, 3.3 volts, we know where that comes from. That's the output of this regulator here. But where does this battery power come from? Well, we just have to kind of trust that somebody connects a battery to this pin and not something else, so it actually supplies power, to tell KiCad the rule checker. So this is a perfectly valid schematic. But if we want to add something just to make KiCad stop whining about this particular rule checking error, you can add what's called a power flag. So if you click P to open your power things and search PWR for power, there's a power flag. And what this power flag does is says, hey, KiCad, don't you worry. Power is an input here. So power is going to be coming in at this place. So you can mark that with that. And then also we'll need to do the same for our ground pin, saying our ground pin is also, like, it's a source of outside power. It's a ground from outside, if that makes sense. That's now overlapping with things, which is really gross, so I'll move it up there. So with those two power flags, now if we run our rule checker, et voila, 0 errors. No more rules that we're breaking, because we've told KiCad, trust us on this one. We'll be inputting power in this spot, and then it can figure out the rest on its own. Do note, though, these power flags, those don't end up on the real PCB at all. They're just phantom things. They exist only for the rule checker, and don't get carried over. And don't have a meaning, like, necessarily outside of KiCad or other rule checker things, I don't think. So there we are. There is our schematic so far, looking pretty good, I think. I will pause and ask for questions. Oh, just kidding. Haha. Can somebody spot what I have forgotten to do in this schematic? Anyone? Eagle-eyed? I've been a bit silly. Just forgot to fill in a bit of information somewhere. Anyone know where? Bum, 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 ba-da-da, bum. The quiz begins. This is marked. This is 70% of your mark. I hope you're aware. Sorry, nobody needs that. Nobody needs that additional stress. We already have enough marks to be worrying about, don't we? Cool. Yeah, it's a bit hidden away. The bit that I've forgotten to do is actually give these capacitors any value. So somebody could look at the schematic and be like, excellent, there's a capacitor here. I don't know if that capacitor should be as big as my entire hand or a really tiny one that goes on this board. Now, granted, I'm sure somebody's going to be able to be smart enough to figure it out, especially from this context of being a linear regulator. But we shouldn't be ambiguous in our designs. So double checking that everything has values. Our resistor, 10K here, 1K there. This capacitor is 100 nanofarads. Then the only other things that need values are these two capacitors, both of which do not have values. So we can check our little data sheet, and it says here, very small, granted, that each of these should be 1 microfarad. So why don't we slap that in? If I go here then, and we can go to our capacitors, roll over where it says C small or whatever, because that's the value field, press E to edit it, and do 1, and UF is how most microfarads are marked in these sorts of things. So 1 UF, and do the same over here, 1 UF. And I'll need to move that so it's a little bit closer again. Excellent. Oh, it's a bit ugly. Disgusting. That's fine. Cool. Okay, so now I think everything is labeled up. That should be fine. Still passes our rule checker. Excellent. I think that's a finished schematic, actually. So that means we get to move on to the next step of things. Before we do, though, I will ask how people are feeling. And we'll probably only get to start the next section. That's why there are 2 sessions on this. Next one will be all about actually creating the real PCB. So, how are people feeling about drawing schematics? Schematics. There we are. And this can be any general questions if you have about schematics at all. I'm happy to answer them if you have any. So I'll give everyone a second to do that. Oops, that's not what I meant to do. I meant to highlight those and move those over because my perfectionism is constantly telling me to move these. How dare you grab my GPIO pens? Oh, and I've done it wrong again. There we are. Cool. One person's feeling okay about drawing schematics at least. At least they've marked on the poll. How are other 2 people doing? One of them's doing great. 2 of them are doing great. Fantastic. How can you choose the value of a pull-up resistor? Yes, okay. Very good point. Or question. I don't really know if there's a great way to do that. I think it depends. You could, if you'd like, do the calculations for it. And in fact, well, the reason that maybe these values are different in different places is because electronics are imperfect. So somewhere on this reset line here that has this pull-up resistor on it, somewhere along that line, there's a bit of capacitance, so it can store a little bit of charge. So what essentially needs to happen, what the pull-up does, or say like what the pull-up does is it supplies a certain amount of current in towards that pin. And that fills it up with positive charge, so it's charged to be a high value. Now what happens when we press this reset switch, there's no resistor here, so it very, very quickly, almost instantly, of course not actually instantly because even this has, resistance because it's non-ideal, all of that's going to flow out, it's going to connect straight down to ground. But if you think about it, this button is pressed and the pull-up is still there, so really what's happening with this reset circuit is you've got, well, and I'll copy these to make it a little bit even like explicitly clearer. Well, that didn't work terribly well, did it? Well, I'll move it here temporarily. So, as I'm defiling our beautiful schematic here, I'll undo it all in a second. What this really looks like, and I realize all I'm doing here is just connecting those reset labels we had, just so it's a bit more visually obvious what's happening. If you press this button down, you have a direct line from your power to your ground. So current will flow through here. Now, what will happen is, depending on the value of this resistor, a different amount of current will flow. So 10 ohms over, well, 10,000 ohms even, over 3.3 will leave only a very, 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 very tiny current. But if you have a larger capacitance, maybe, you might want this value of the resistor to be lower, so that current is greater, so that when you release this button, it can more quickly switch it back to a high value. So picking pull-up resistors gets into thinking about non-ideal components, I think, and using, again, Ohm's law to calculate the current flow and like the voltage drop over this resistor, for example. So that's a bit squirrely. I think if you use either 10K or 4.7 ohms, it's entirely fine. My honest recommendation would be, if it's between 4.4 or 4.7 and 10 ohms, pick whichever resistor you have the most of laying around your house, because it's honestly probably the best way to do it. Cool. Does that answer the question about pull-up resistors? How you pick their values? Awesome. Cool. Nice. All right. Cool. We've got about 17 more minutes, so I'll vibe along, and we'll do one last next step before calling it a day and coming back. Oh, actually, after Easter even, to create the PCB itself. Wow, that's one heck of a cliffhanger, isn't it? Take that, fools. Get cliff hung. Awesome. Cool. So, we finished with the schematic part. If somebody just wanted to recreate our circuit, but wasn't looking to create a PCB, they could do that. I've done this, for example, for breadboard circuits I've made, because I've sent these breadboard circuits places where I don't exactly trust that they will stay in one piece. So if they come apart or something, this is just a nice way to digitally design a schematic so I can remember how everything's connected. But to turn this into a real PCB, we need to tell KiCad how big all of these different components are actually going to be and what shape they're going to be on the PCB. So this is another big library of components it has of footprints, or what they're called, because these little things, when you put them on a PCB, have little footprints that they leave, and that's what we solder them to when we're building the actual board. So, to pick all of those, the tutorial does this in a bit of a different way, so I'll show you how it does that, and then I'll do it in, I think, what's a bit of an easier way. So if you go over a particular component, like our microprocessor here, press E for edit. Well, just kidding, I wasn't clicked on my KiCad window. If I click on that KiCad window and then do E, you can see a bunch of data about it, one of which is here, this footprint. And you can see there's our SOIC 14 package that we saw on the data sheet a little while ago. So it has already figured out automatically the footprint of this chip, because we've given it a very particular chip. In fact, it's probably also done that for this other microchip over here. If we roll over that, press E, you can see, yeah, that already has a footprint. It's the SOT 23 footprint again. which is good. We remember seeing that in our data sheets. But for things that are more general, that come in all sorts of different sizes, like this resistor, for example, there's no footprint here. So what we could do, manually find the footprint, do this little browse thing there, then look through all the different options and pick things and save them. But a nice way to do that for the whole schematic at once, because we'd have to do that for every individual component, which would be a bit of a drag. Instead, you can go up here, up to your top bar again. There is a... Do I actually remember which one it is? Yeah, there we are. To the right of the ladybug, there's assign PCB footprints to schematic symbols. Is that in the tools as well? Yes, assign footprints, second to bottom. There we are. If you click on assign footprints, or that little button to the right of the ladybug, it will give you an error because it's trying to find something that is a library I didn't include, which is fine. That's okay. That's something I'll just get probably. Probably won't be an issue for you. Cool. All right, so this has opened a second window for us. It's a bit hard to tell, but in the background, it's now highlighting the components that we highlight over here. So I've, in fact, entirely managed to push away that middle bit. So if I click on, say, switch 1, it moves us in the background to switch 1. So you can always, like, Alt-Tab. In fact, that's the better way to do this. Just kidding, because they're both part of the same program, aren't they? So it doesn't want to Alt-Tab between them, yeah, because they're both under the KiCad card array. Well, point is, you can see which component, like, these labels correspond to because it highlights them in red on this side as well, which is nice and convenient. What do I not need here? I don't need 2 of these windows, so I will move them away. Okay. Nice. So you can see, like I said a second ago, our 2 microchips already have their footprints assigned, which is fantastic. We need to assign footprints for the rest of these things. This is a bit of a tricky part because there are lots of different sizes and it's hard to know which ones are right if you haven't just had experience with it before. For what it's worth, let's see, RS components, for example, you could look at for components. And they sell things like, oh my goodness, we are in the United Kingdom. Please take me there. Excellent. You could look for things like resistors, fixed resistors, surface mount resistors, things like that. And you can see, wow, all these different sizes. This, for example, is, well, actually, this is an excellent example, these first 2 things. I guess it's because they're the most popular, of different footprint sizes. This one is a size called 0603. That's one size. This one is 0605. Those may look identical to you. That's because they've used the same picture for both and changed the number. In real life, those are different sized components. So they aren't really interchangeable. Sometimes you can connect the smaller one to the bigger pad. But the point is, here you'd want to find, okay, your resistor of, we had 10 kilo ohm resistors, right? So over here, I'll make this a bit bigger for you all. Over here, we can go to resistance filters and say, okay, I would like a 10 kilo ohm resistor, right? So I can scroll down to 10 kilo ohms, which is really far away. Really, really far away. Okay, we've gone too far now. 10 kilo ohms, you can see there's a bunch of options, 448 10 kilo ohm resistor options. Apply this filter. There we are, 10 kilo ohms, and you can see all the different sizes they come in. So we could still pick either 0603 or 0805, or even 0402. Yeah, so there's a bunch of different sizes. But you basically need to pick the components you want first, then pick the footprints that will match. So you need to think about what components you're actually going to solder onto the board before you assemble the board itself, if that makes sense. I'll be following along with the footprints that the tutorial uses, so that way it keeps things consistent. And if correct, they are using they're using metric footprints. They're using an even different one. Oh, no. Okay, that's fine. Yeah, they're using 0805, it looks like. So a second ago when we saw, well, that didn't get me where I wanted to be. A second ago, this 0805, this is the size components that we'll be using for most of the things on the board, because these are a bit bigger than these ones, so they're easier to solder, I guess, which makes sense. So we'll hop up here. Start with our 10 nanofarad capacitor. So for that capacitor, sorry, not 10 nanofarad, 100 nanofarad. If you click on it once, basically, you can then, well, it's selected there, and then over on this side, you can look through different categories like capacitor surface mount, which is SMD, that's surface mount device, what that stands for. then you can go through and find the footprint that you're looking for. So here are all of these capacitors here. There are a lot of them. We can filter them, though, I think is what this up here is. And we can filter for 0805 or 0805. That's what I was looking for. 0805. Oh, hello. Goodbye. Managed to not do that very well. Hop back to assign schematics to PCB symbols. I don't entirely know what I've done there. Oh, I just forgot to turn that on. And enter, of course, just closed it out because it was probably hovered over that. Okay, fair enough. 0805. Oh, right. Of course, there are no 8005 battery holders, so I need to go back to capacitor surface mount. There we are. 2 of them there. There are 2 different pads. I wonder if I double-click on these if it'll show us them. The answer is no, it will not. It'll just select them. Oh, if you right-click on them, you can view them. So, that is an empty footprint, my dude. Cool. Oh, maybe that's just because it's viewing that. So if I do that and then view footprint. Yeah, okay, there we are. That makes more sense. So there's an 0805 footprint for if a machine is soldering things. I think hand soldering, the difference is you have slightly larger pads to solder onto. So I'll select that one and do view footprint for that. It's probably just open it in the same window, hasn't it? Yeah, it's open it in this one. I will admit it is hard to tell just from looking at this that this is much different from the last one, but we'll roll with the hand soldered one since this component board hypothetically would be hand soldering. So click up on the 100 nanofarad capacitor and double click the hand soldered one. I've also already accidentally assigned our second capacitor to be the same. I believe that will be fine. I'll double check. So you can assign them to be all different or the same, depending on what you're looking to do, to be honest. Yeah, I think these capacitors, they might need to be slightly... Wait a minute, am I being silly? No, yeah, those are slightly bigger, so sometimes you'll have trouble finding ones that are tiny enough. Sorry, that didn't make any sense. Sometimes, if you're looking for a large capacity capacitor in a really small form factor, they just don't exist, so that's when you would go to RS components and see if you can actually buy them. Because, for example, if you wanted like a 1 farad capacitor, which is like an obscenely massive amount of capacitance, in something this size, well, that's... You're very out of luck. That will not be possible. So yeah, that's you want to use RS to check what's actually possible. Again, find your things on RS first, then you fill in these footprints kind of second. So yeah, in this case, we're going to go with same size capacitors for both of those hand soldered things there. Now let's think about what we want to do next. I think it might be worth doing the resistor, I think. So for our resistor, which is R1 and 2, we have 2 resistors. We can check what those are for again. One's a pull-up there. The other one is a LED current limiting resistor. And we can set those to a certain size. To be honest, I think we can get away with the exact same size because we've already seen an RS. In fact, our first search was finding a 10 kilo ohm 0805 resistor. Oh, by the way, resistors. You can find really small resistors of really high resistance values. Keep an eye on this wattage number at the very end. That's how much wattage they can tolerate before they burst into flames. Now granted, this is a bit on the safe side. You can probably put a little bit more power through it than that amount before it, explodes. But the consideration to keep in mind with resistors is make sure you know the amount of current you're running through them and that it can tolerate that amount of current. Remember, wattage is voltage times current. So here it's fine because we have 3.3 volts, but we're passing incredibly small amounts of current through it since it's a pull-up resistor. So that one, fine. But if you had something that needed more power dissipation, like if you were building a heating system, this might not be what you're looking for. You'd be looking for something much larger, so it'd be in a larger case probably. Like this, for example. This is an actual, like, round kind of resistor instead of a flat one. Totally different package shape, but this one can tolerate up to 0.2 watts. This one can tolerate a whole watt. That's probably a massive on-surface one. So different power ratings. That's important to keep in mind as well. Cool, we have just 5 minutes, so we can probably just get the rest of these footprints knocked out. Resistors then, you can go over here to resistor somewhere. Resistor surface mount device, so resistor SMD. I'm still filtering for 0805 up here, so you can see 0805 here. Hand solder option, there we are, there we are. Those footprints are set. Those are very, very similar looking to the capacitor ones. In fact, I'm not sure what the difference between them is, because they are like the exact same shape, so it makes sense for them to be the same. That's the resistor again, if I do this and then that. Yeah, they look identical to me, to be honest. But they can vary depending on, obviously, if you pick different footprint sizes. LED, that's what we need to do now. What size we want to do the LED? Well, fun fact, I'm pretty sure you can get 0805 LEDs. So if we search for LED, yeah, LEDs. And then here, again, you want to look at mounting type. We want to do surface mount and apply that filter. It'll go ahead and think about it. There's a bunch of surface mount things, and we want our package to be 0805, because we are incredibly original, of which 6 exist. Fantastic, that's enough. And there we are. There are some 0805 surface mount LEDs that we can pick out. So again, find your shape here first, then your footprint. We are obviously keeping things very simple by using as many 0805s as we can get our hands on. So up here, let's see, I need to find LED, SMD. There we are. Wow, once again, 0805, hand solder. This one should look different, I think, maybe. Whoops, sorry. Nope. It's 0805, looks the same. Fantastic. Nice. And programming connector. So we need to go down to connectors down here, or actually up even. Pin headers. Now these have different, what are called, ooh, what do they call them? I forget exactly what these little numbers here. Pitch. Different pitches. So the pitch is the distance between like the pins. The most standard one, and it's really annoying because it looks terrible in metric units, is this one here, which is 2.54 millimeters. That's because this is originally done in like fractions of an inch or something, which is disgusting, but oh well, can't win every battle. Here you are. You can see a bunch of different options. For example, if you looked at, say, a horizontal one, that'll look like one thing. So there you can see this footprint has left room for horizontal pins to go out this way. We're not interested in that, we want something vertical, so we're going to do this vertical one here, do that footprint. That's kind of what we're looking for. I happen to have looked for 1x4 ones, which is not exactly what I wanted to do. But that's fine. We do have 1.4s to fill, don't we? Oh yeah, that is what I want to fill here. Yeah, sorry. It's automatically detected which connectors have enough pins. So yeah, this GPIO one, I do want that 1x4 vertical, so I'll do that. Do the same with the GPIOB. Then we have our programming thing. This one is different, remember. This is 2x6. So it's automatically figured out here that there's these 1x6 options. So there's a 1x6 option. We don't really want that. We wanted a 2x6. So here are those options. Here's a vertical 2x6. That looks like what we want. We can plug in our little JTAG programmer to that. So we'll go ahead and select that one for that. Battery connector. Ooh, this is one that the tutorial did in a different place and I ignored. Battery connectors come in all sorts of weird things. They used a JST connector, I believe. Yeah, so you can go to connector JST. Here's a bunch of different ones. They come in a bunch of different sizes. This you'll just have to look at and see what your battery uses, honestly. But we'll have to use the right one. I'll fill this one in later. And we'll go to the switches real quick. So buttons, button switch. We're going to do through hole, actually. So this one is not printed directly on the surface, but actually goes through the board. And we want to find a 6mm push switch, because that's the one that they've used again here in the tutorial vibe, but this is just a regular button. Most buttons have like 4 pins, even though 2 of these are the same on all of them, so don't worry about that. Yeah, see both 1 and 1 here. So these are the same pin, and these are the same pin. They're just in 2 places. So we'll fill that one in, and there we are. That is our footprints all set up. So I'll real quickly jump back, just so for anyone following along, we can get the battery connector. So the battery connector is a JST connector, but there's a bunch of different ones, and this particular one being used is a 2mm vertical one. So okay, so if we go to our battery connector here, connector JST. I've already lost it. There you are, JST connectors. We want a 2mm vertical. Oh, there's a lot of options there. Is it a VH? It is a PH. So yeah, they come in different standards. Like you see, these are PHs here, these are VHs. Those are quite annoyingly very different things. So if I look at this one here, this is the one that we'll end up using. This is a one shape of connector, but this VH, for example, is a different shape. See, it's much taller, this one, so they're physically incompatible. We want this one here. That works for me. There we are. Apply, save schematic, and continue. And now we're done. All of those have footprints. You might not be able to tell here, because it does not show you here. But we will see it next week when we lay out our PCB. It'll take all of our connections and splat them onto our PCB, and it'll be our job to arrange and connect all of them. So I've run slightly over, so what I will do is first ask, well, how are people doing? Do you have any questions about anything that we've done? Because I'm around for as long as you need. So how are people feeling about things? So there's your poll to answer, and then I will also send, because I think me, in my infinite wisdom, and by infinite wisdom I mean last minute preparation, I have prepared the feedback form ahead of time for you even. So don't even have to send it to you in the wrong session. So there we are. We've all survived this session. Let me know how tolerable or terrible it was. Philip has said, the component size stuff seems hilariously tedious. Yes, by far, that is the worst part of building a PCB, is figuring out what size things need to be. Everything before and after that is easy, like drawing these schematics. Afterwards, just drawing them in a little PCB thing. Yeah, it's very, very tedious to find the size of these things because, well, only some sizes actually exist in the real world, so you constantly need to be checking for real products that actually match your design. But yeah, I agree. It's a bit tedious. At least KiCad helps us, or KiCad, sorry, for some of the simple ones. But yeah, it does get easier with experience, especially if you have like components sitting around in your house. So if you've made a couple boards and you have a bunch of 0805 resistors that are the right size, then you can just put it in. But yeah, definitely gets better with experience. I remember walking into the Avalon meeting with these people, and they just started saying, oh, you need an 0805 for that, or an 0603, and I was like, these numbers mean nothing to me, because they're hardly meaningful numbers to begin with, so yeah, it just takes experience. And is surface mount resistor more popular than the through-hole type? Depends on what you're doing. For things like this that are really tiny, yes, yeah, surface mount resistors are generally more popular. In fact, for anything small, surface mount will almost always give you smaller components with like the same abilities. So I'd recommend surface mount when you can manage to solder it. If it's too tricky to solder, then through hole is the way to go. Or if you have through hole sitting around, design it that way. That works as well. You can just assign a through hole footprint to like this resistor here. Cool. Nice. Everyone's given a thumbs up. They're feeling good. Hopefully people have given the feedback form a look. Did I paste it in the Google one? Yes, I did as well. Awesome. In that case, thank you for coming along. Sorry for running about 4 minutes over here. And hope you have a lovely Easter holiday. And then we'll come back and route some PCBs, which would be kind of fun. I do find that part the most fun part because it looks very pretty. If anyone's interested in looking for like 30 seconds at a really cool thing, I'll show you the motherboard that I built for the Avalon project. So here's my baby circuit board. So you can see quite complex once you all lay it out. It has, this is the motherboard here. This is the big ring of LEDs that it'll power so the camera can see through the middle of this hole. So you see you have these big power tracks here that you have to lay. Green and red means they're on opposite sides of the board. There's the processor. There's a bunch of communication stuff. So this is the fun part, I think. It ends up looking really cool. And you can even view it in 3D if you want, which is kind of fun if it loads. Aha, there it is. Yeah, so it's really cool once you get to that stage. That's the coolest part, I think. Anyhow, I will free you all. Have a lovely Easter holiday. If you have any questions, I'm sticking around. Otherwise, see you all next time. Awesome, yeah, thanks for coming. Frohe Ostern. Yeah, see you. Excellent. That's fantastic. I fooled somebody potentially into thinking I'm German. What do you think about that, recording people? I'm not, in fact, German. I'm incredibly American and taking German at uni. Anyways, see you next week.